Good morning. So it is my pleasure to present to you the ARENA project. I thank Paul for being so enthusiastic about our project, and I hope we can make all his expectations, meet all his expectations. So I'm Dimitri Staessens, and this work is with Edward Grassa from ITOCAT, Miguel Pons de Leon from Waterford, Francesco Fagertun20th from Networks, and Didier, who is the coordinator from iMinds, is also here. So I'll quickly give the outline. So first I'll just state the project goals and the structure. I'll introduce the partners to you because this was also asked by Paul. I give a very short introduction to ARENA, basically just the main concepts because tomorrow there will be a longer presentation just focusing on the ARENA, the recursive internet architecture tomorrow. And then I'll give you a very short update of what we'll ask from you because our goal in the ARENA project is also to get some feedback from the NRENs, and we will put up a survey for that, and I'll give you an introduction on what we expect from this survey and hope to get out of it. So first, the project goals and structure. So actually the main goal of this project, there's only one, that is to demonstrate to you what ARENA can bring to you in an NREN environment and why it's better than the architecture that you currently have. To do this, we'll have a number of sub-goals. So first we'll build a good use case for the project, which will be based on your inputs. We'll do some desk research comparing different architectures, not only ARENA, but for instance the extensible internet architecture and maybe also SDN, forces, things like that. We'll build a test setup, perform lab trials in our lab environments and give a demonstration of how ARENA would work in this environment. And one of the other main goals is to disseminate research, so we'll organize a workshop joint with JRA1. And we also aim high-profile publications as part of the GEONT project.
What do you mean with ARENA?
ARENA is the recursive internet architecture. I'm sorry that I didn't make that clear. So it's a clean slate architecture, and I will tell a lot more about it later. So the project structure, we have 4 work packages. So I'm maybe that you can see, but we have 4 work packages. One is the technical coordination, one is the specifically targeted dissemination and the workshop organization, and there are 2 technical work packages, work package 2, which will do the comparative analysis of the clean slate network architectures, and work package 3, which is really the bulk of the technical work, which will do the lab trials, do the prototype and such. So there are 2 external dependencies. One is actually you guys, so the GEONT and NREN, which we will need to do the use case, to build the use case. The other external dependency is the Irati project. The Irati project is also focusing on ARENA, and it's doing the first real performant implementation. So we have taken the Linux kernel, we threw out everything that's in there regarding TCP/IP. Well, actually, we didn't throw it out, but we bypassed it, and we are implementing the ARENA stack into the Linux kernel. So the task structure of work package 2 for the ARENA is, so the first task is understanding GEONT and NREN requirements, where we will do a survey among the NRENs, so among you, and design the use case for work package 3. And then there is a survey of the state of the art, which was one of the goals of the clean slate design call. So where we will compare ARENA to SDN forces, but really tailored to the use case of NRENs. And then there's assessment analysis, so the strength, weakness, so it's a SWOT and a PEST analysis of the different architectures. So work package 3 is the use case study and the lab trials, where we will apply ARENA to the NREN requirements and design an experimental setup for testing our architecture. So there's a specific task of adaptation of the software. So the Irati project will deliver us the software, but it could be that some aspects which are the use case of Irati is a cloud provider. So we have Interout in there. So we have a very specific use case for them for mobility of virtual machines in an inter-cloud operator. And it could be that the prototype just isn't completely tailored to what we want to do with the NREN. So the differences in use case may be that we need to modify the prototype. That's task 3.2. And task 3.3 is then set up conducting the lab trials, the analysis. And we have 2 test beds there, one at iMinds and one at ITOCAT, and we may use the GEONT test facility, which was discussed during the negotiations. So the experimental testbed from ITOCAT, which is part of the Ophelia, if you know Ophelia experimental testbed, which has basically the most interesting infrastructures. They have 5 servers which can run, 5 high-end servers which can run a number of virtual machines, and they are interconnected by open flow switches by NEC. So we have 5 open flow switches, and we can control the topology of these switches, not of the switches, but the virtual topology between the virtual machines using these switches and using open flow. So they have an open flow controller which can set up different topologies. There is a tunnel towards our testbed in iMinds, which is part of Ophelia, and of course interconnection with the internet. Then the other testbed is our testbed, which is the iMinds virtual wall. We have 3 now. Well, actually, it's a complex story. We have 2, which were first 3, but we merged 2 of them. But this is the picture of the oldest one, but it's more impressive because this has 20 displays attached to it. So basically, it's our 100 servers, which are interconnected by one very big switch. And this very big switch is using VLANs to control the topology between these different servers. So it's not OpenFlow based, because when we were building this, OpenFlow wasn't there yet. But it basically is the same functionality, and it's based on Emulab. So Emulab, the architecture looks like this. So we have one control network which is connected to all these 100 PCs. And then we have this very large switch which we can program to set up a topology. We have external power control, which is very handy if your machine locks up or doesn't boot anymore, especially if you're doing kernel programming. If it panics, we can just remotely reboot those nodes without having to go to the test lab. So that's an introduction to our facility. So the project timing, IRENA is an 18-month project. We have actually 2 deliverables. One is a final report of everything that we did. The other deliverable is the software prototype, which will be publicly available and open source. And then our goals are to have international conferences. We also want to have journal publications and the final report of the project. So the project partners, I'll quickly go through. So first of us, there's us, iMinds. So this is the organization formerly known as IBBT, if you know those. So just a name change. There was no big thing there. So it's just IBBT, which is now called iMinds. We are in the future internet department of iMinds. There are different other departments like security departments. But in this future internet department, there's us, IBCN, at the University of Ghent. There's also wireless and cable at the University of Ghent, which is all in Belgium. Actually in the northern part, Flanders. So there's no IBBT or iMinds is a Flemish institute, not Belgian national. There's PATS in Antwerp from the University of Antwerp, and EDM, which is in the University of Hasselt. So these 4 are part of iMinds, and we, IBCN, are doing this IRENA. So IBCN quickly is a part of Department of Information Technology of Ghent University and part of this future internet department of iMinds. Our results quickly in our group, we have roughly 1,400 publications, 75 PhDs. We have won a number of international awards, and also one of the goals is to start spin-off companies. So we have 6 spin-offs. And there is a very strong involvement in informatics courses that we give at the university. So basically on informatics, software engineering, and networking. So roughly the total staff is 135, where we have 46 professors and postdocs, and 58 PhD students. So this is a large group, as you can see, all the people are here. So there are a number of research domains. I'll go just the people who are involved in this project are in this first research domain on network modeling, design and evaluation, and it's led by Professor Mario Picavet and by Professor Kolle. So there are a number of other groups, but they are not involved in the IRENA project. So international presence, we have 25 international researchers from 20 different nationalities. We also collaborate externally with other universities, like in Berkeley, Stanford, NICTA in Australia, which is more on the test beds. They have this OMF. We work together with Keio University, where we have, it's a sistership university partnership, something like that. So at least it's official, because they gave us a very nice certificate that we are collaborating together. And we also participate in a lot of international research projects from FP7, also some other funding bodies, but the ones which are important to this, so we have IRENA here. The other one on is IRATI, which is also on RENA, and we also have expertise in architectures like from Spark, Strongest, which was an optical Oasis on optical access, so we have a lot of experience. Euler is a project which is on greedy routing, geometric routing, so there's plenty of experience at iMinds in future network architectures. Oh, this is moving, I didn't know that. So then the next partner is I2CAT from Barcelona. They really are also a research institute, so that they also want to fill the gap between industry and the university and the research. So they have similar goals as iMinds. So they have, it's a little bit smaller, so they have 27 researchers, and the person who is involved in IRENA is here, Edward Grassa. Don't worry if you see him, he really has a body. It's just not a floating head. But so he is the technical coordinator of the IRATI project, which is of course closely related to IRENA. So they have more expertise in RENA than us, because they already work together with John Day since 2009. So John Day is the guy who developed and invented RENA. So they have already published a number of papers. Actually, we have a very nice recent publication in IEEE Network magazine on the architecture and what we are doing in IRATI. So they already have a prototype of RENA, but it's based on Java, which is a bit for IRENA our fallback option. But our goal is to really use the IRATI project prototype, because it's a lot better. It's really built into the Linux kernel, which is a lot more performant than a Java application or script. So they already have the experience in designing the software and architectures for management control of optical networks, because they work together a lot with UPC, which have the adrenaline testbed is at UPC, and the experimental testbed is at I2CAT. So then the third partner is Nextworks, which are also partner of IRATI. So both, well, iMinds, I2CAT, and Nextworks are all in the IRATI project. So they are a smaller company, so an SME, and they have actually two tracks. So maybe I have it here. So they actually have two divisions. So one is products, where they are building control and automation systems. Basically, one of their main businesses is building in boat networks. So they do these large yachts, which are built in Italy, and they do the internal communication. So all the video systems, the domotica actually, but in large yachts. And they also have the technology domain, and the guys who are involved here are in the architecture group at Nextworks, so the architecture division. They work together with a lot of partners. They are involved, so in the most important ones are Alcatel-Lucent with Ericsson, with NEC and Juniper, because they are all Interroute also. They are all involved now in these RENA projects, also Telefonica in an upcoming project. And then together with a lot of research partners like Bell Labs, NEC Labs, iMinds. So the knowledge division, they have a number of R&D tracks, and this recursive internet architecture is one of their R&D tracks. So they are involved in a number of current running EC-funded projects, and if you look, they really have a core expertise on GMPLS, PCE, which is network control, and then they really built it towards this new architecture arena. The final partner is TSSG, so it's Waterford Telecommunications Software and Systems Group in Ireland. They were founded in 1996. They have similar staff as iMinds, so roughly 100, between 100 and 150 people. They also have the goal of starting spin-ups and really bridging the gap between the industry and research. And currently they are also involved in a large number of projects. As you can see, 39 projects are currently running there, and they completed 148. So the main area of expertise, they have also been collaborating with John Day at the University of Boston on RENA. together with i2cat, and the collaboration will now include IRENA, this project, and also an upcoming project in FP7 Strep, which is called Pristine. So now I'll quickly go to RENA. So what is this recursive internet architecture? Because that's probably a question that you've been asking for the past 5 minutes. What am I talking about? So actually the groundwork has been laid in a book by John Day from 2008, which is called Patterns in Network Architecture. And this is, there's no mentioning RENA in this book, but it just brings out the basic concepts which later evolved as of 2009, 2010 into what is now the RENA architecture. So some background. So when they were developing what is currently the internet, there was in '72 there was a group started to really with the goal of building an international transport protocol. These were guys from ARPANET, from Cyclades in France, and they came up with two solutions. So they came up with something called INWG37 and INWG61, and the one was based on TCP and the other was based on the Cyclades transport. I don't know what the S stands for. And actually, they saw that there were differences between these two proposals, but there was a lot of things that they had in common, and they just looked at the commonalities and they came to a synthesis which was proposed and voted in 1976, which was called INWG96, and this was the architecture that they thought that the future internet should have. And it was actually they had 3 layers. So they had a data link layer, which we still have, a network layer, which we still have, and they had an internetwork transport layer. And these layers were just had different scope, and each had addresses. And this is not the current internet. We don't have this. What we have right now is what was done in '83 at Flag Day. We have the internet, and there is no internetwork layer. We don't have an internetwork address. We have a network address, which is IP. You have a data link address, which is, for instance, the Mac, your Mac addresses. But we don't have an internetwork address right now. So you could say that BGP, but it's using network addresses, which are IP. So the transport layer really has no addresses. TCP, you don't have a TCP address. You have a TCP port, which is trying to identify your application somehow, but it's not an address for your application. And the transport layer just provides end-to-end error and flow control. So your end-to-end, your flow control is actually here at layer 4. So which doesn't really make sense at all. If you have congestion somewhere inside the network, you shouldn't try to solve it 4 layers up and 5 networks beyond. And IP does the relaying and multiplexing. So IP is forwarding your packets towards the correct destination. So, but that's not really it, is it? I mean, you have been running networks. The simple OSI model has 7 layers, of which 4 are, well, you have the application layer at layer 7. Then you have the presentation and session layers, which only professors know what they really do. And then you have the simple model, which is you have a physical layer, you have the data link layer on top, the network, and then the transport layer. But as you all know, currently you can have some mess like this, where you have layer 1 over layer 2 over layer 1, which supports another layer 2. You have an MPLS layer 2.5, which is really a pseudo wire for another layer 2 protocol, which is running IP, which is really encapsulating another IP layer. Then you have UDP on top, but somebody's running a VLAN, which is of course again layer 2, which is layer 3, and then you have your transport control protocol, which is really solving some congestion down there below. And then you have your application on top, which is, well, it's quite difficult to manage a network stack like this, and probably you have experience doing it, but it's not really a clean solution. So this really simple model of OSI, which has 4 or 5 layers and 2 layers that nobody cares about, is not really what we have right now. So you have a very complex network stack, which is very difficult to manage. For instance, what is quite difficult to do in IP is multi-homing. So the main problem is that the network doesn't really know that your computer has 2 interfaces which are in the same host. So if you have a failure, if you have, for instance, this host which has 2 interfaces, 2.1 and 2.2, your interface towards 2.1 goes down. Then if you are communicating through that interface to the host, then if you have a failure, your IP will say that it's not reachable, and somehow if you want to do multi-homing, you have to relay some information to this host, which is not, that is saying that if you cannot reach that application at 2.1, send your packets to 2.2, but it's not really the network which is doing your multi-homing. It's just you have to manage it end to end or somewhere at the intermediate points in the network. So the fundamental issue is that the network is calculating a route to a place on the path to the destination, but not the final destination. You don't want to reach that interface. What you want to reach is an application or a process which is running on that remote host. That's what you want to communicate with, not with that interface. Who cares about that interface? So yeah, you don't even have an identifier for the node or the application. So it's really a bit skewed. And it comes from the old days when you had only one machine with one interface running one telnet protocol, and then it was very happy. If you reached the machine, you knew it would be delivered to that application. But currently, and especially with virtualization, you have a lot of applications running in the same host, and you really don't reach them. You just drop your stuff off at the interface, and then it's internally in the host where it is trying to figure out where to deliver the information to. So is it hard to fix? Of course not. You just name your nodes in an independent namespace. You calculate the routes based on your node names, and you just select which interface you want to reach to a certain node. So if I have two interfaces between two machines and I have two cables, I can select which cable I can use. That's how it should be. And they could have solved this because they knew about this a long time ago when they went to IPv6, but nobody seemed to care because IPv6 still says that an IPv6 address of all types are assigned to interfaces and not nodes. And if they would have assigned it to the nodes, they could have solved a lot of issues. So another aspect which is currently a little hard to do is mobility. So we see it as just a very dynamic version of multi-homing, where you have one multi-homed device of which most of the links are always failing, and only one is working. So if you're moving, so all the links that you are not using are actually failed. And so your host moves, it acquires new points of attachment. So a point of attachment is where your interface is relaying to the network, and it just drops your old points of attachment. So you just need to do routing updates in the network to do mobility. And if you do your naming and addressing right, then mobility is supported without the need for special protocols. So that's where RENA just had all these concepts which we learned about in the last 40 years since we are using TCP, or it's 30 years probably, since we are using TCP, is encaptured into this architecture. So do we have application names in TCP IP? Well, you could say that a URL could be something like an application name, but basically Giant.net is a synonym of an interface of a host because it translates to an IP address, and an IP address is actually sort of, it's not really a network address, and it's like a synonym again for a MAC address because it assigns the same piece of hardware, the interface, and then you have the port number, which is the endpoint of your TCP connection. So again, you have a fundamental issue, which is that you have a static binding between layers. So you are not routing on that. If you see the application name as Giant.net, then you would try to route at least on a binding which is only available for Giant.net. You would give that a more easier address and try to route on that. But now you have to do it at a lot of layers below. So point of attachment addresses, interface addresses, which are currently IP addresses. And if your application wants to move, what if your connection crashes? You have to update your DNS entry to a new interface name. It's really a lot of work. And in general, if you would just address based on this, on the information, and I think content, these ICN networks have some of the ideas right, so that you should be able to route on application names and not on interface addresses. So if we wrap this up, what would be a good architecture? If you have application names, you have node addresses, you have point of attachment addresses, and then routing is really a two-step process. So you would calculate a sequence of nodes that you need to reach the final host. So your application name would say, I need to find this application. It tells this to the layer below because it has only communication to this layer. It says, I want to reach this application. Then this layer will use a directory to figure out, so only upwards, okay, this application is attached to this address, to this node. It will route through the address, and every hop needs to figure out how to reach the next hop. So this all comes from operating system terminology, which is called IP, inter-process communication. And the big difference between networks and a computer is that in a computer, your path between the two processes will be quite fixed. And in networks, you need to specify the interfaces because you can have multiple routes between two hosts on the layer below. So the two-phase process is that first you calculate the sequence of nodes, and then you select an appropriate path. So the naming needs to be, application needs to be location independent, so that at least you can move the application without having to change the name, and the network can find it. So if the hosts, for instance, move from this router to this router, the only thing that you need to update is the directory. This IPC layer would just need to know, okay, my application is now at this point instead of this point. So it's an update of one entry. And you could use something like DNS. It's not entirely new, but it's not like how it works right now. The node addresses need to be location dependent because, of course, you want to be able to find them. So an address for a node is a locator. And you can optimize routing if you have hierarchical address, for instance. And you need to name your point of attachment, so your interfaces need names as well. So this is RENA. So how many? I have 5 minutes left. So the structure is recursive, so you can build a lot of these layers. Each layer has a single type that repeats as many times as required by the network designer. So every layer has exactly the same function. You don't need to implement all of them, but there is no layer that will require more functions than what is defined in a diff. At least that's the goal. And it's called a diff because it is a distributed application that performs inter-process communication. So diff stands for distributed inter-process communication facility. So it's really the same functionality that you have in your kernel for communicating between applications on the same host, on the same machine, and extended towards a network-wide environment. And this yields a theory for networking, and it also gives an architecture, not the implementation, but the architecture at least scales indefinitely. You can stack the network layers on top as far as you want. I think I've said most of this, so I'll skip this slide. So what is inside one of these layers? These are all the functions that were currently defined as necessary inside a network layer. And they are organized a bit from depending on the data packets and needing to be performed at a very low level per packets performed. For instance, your SDU delimiting or PDU delimiting could be, SDU is actually the data you get from the layer above, and the PDU is your protocol data unit inside your layer itself. But you need to do the limiting. So if you get a large packet from the layer above, you could be that you have to cut it up in smaller pieces. This is stuff that needs to be done in the hardware, very low level, very fast. And then you have data transfer control like retransmission, AX, flow control, throttling, stuff like that, which. So basically, the data transfer is the same functionality as what would be in UDP, and data transfer control would be functionalities that are in TCP. And the big point is that they separated these into two protocols, data transfer and data transfer control, in a way that all the data transfer is dependent on the information which is in the packet. You cannot do a CRC without knowing what is the data in the packet, because you need to compute the error correction information based on the data itself. And data transfer control, you don't need to know what's in that packet. So if you want to do retransmission, you just retransmit the packet and you don't care what's in there. So these mechanisms are separated based on this main function or this main distinction, that functions that you need to know what's in the packets, you are depending on the data, and functions which are independent of the data. If you go further, you would have your resource information base, which is really taking, centralizing all the state that you need in your nodes to perform the forwarding. You have a number of functions here. For instance, this is a let me go to the next. So, for instance, this CEP is actually a phase that your applications go through, but I won't go through them all because I don't have time. But for instance, if you have two applications that want to communicate, you set up your flow. Before these applications communicate, they have one additional phase where they just will synchronize some state. So let's say you have a web server which is using HTTP. It will connect to the client, but before they can communicate, they need to say, okay, which HTTP version are you going to use? Stuff like that. So they need to synchronize a little bit of extra information. And all these phases have been thought through very far, and we try to identify all the small steps from in principle that you require to do to have two applications or two processes communicate with each other. The next step is the shim diff. So of course there is no current RENA hardware or stuff like that. So what we need to do is give this API which we have between these new layers, these new network layers, and build them around what is currently existing. And we call that a shim diff, because it doesn't have all the functions that we require to be a complete layer. We just expose what is currently available in the non-complete, incomplete, for instance, Ethernet layer. So in the Irati project, we are building two of them. We are having a NATO 2.0, so a VLAN. It's so we give the RENA API around VLANs and also over TCP and UDP. And for instance, over VLAN, you cannot do retransmission. So it will, by definition, be an unreliable network layer. I think I have two more. Okay, so the example, I skipped that. So there are some key benefits. So it's easier to do mobility and multi-homing. We have support for QoS. We have improved security because you don't have any interlayer dependencies. So all the layer separations are clear, which just you don't know what's on top of the layer. So if you can snoop, if you can hack into one of these layers, you don't know which is the layer above. You don't know the packet structure. You don't know the addressing scheme, which you do know right now. You just look at the ether type and you know which kind of protocol you are following, and you can just go up the stack and analyze the data. In RENA, that's a lot more difficult. So are we ready for a simpler future to get rid of all this and just go to RENA, where you have diff over diff over diff over diff, and your interfaces would look a lot easier? So you don't need to migrate, you just need to adopt. So you can build these layers in between what we have right now, and you just adopt them when you think they are useful, and if they're not useful, you don't. But in the end, you would have your physical media, all these RENA layers, and the applications on top. So there's a timeline here. I'll go skip that. So 1 minute. So, well, actually, no, I won't skip it. But so the RENA project, one of the main goals is really if we want to, so the NRANs are, as said in the morning, the more innovative players in the networking market. So what we really want is that you have the NRAN prototypes towards diffs supported by the NRANs first, and then it gets supported by carriers towards all RENA networks. So that's our final goal, or that's how we see an optimistic future for RENA, that it would be deployed. And the NRANs, we think they play an important role. So we'll have a survey. The goal is to build the use case. I'll skip this. So, but I'll just go through this. So the basic thing that we want to do in the survey is to have a look at your current application services. your current operation services which you need for the network and try to understand them to build our use case, and then have a look at the performance and the architecture of your current infrastructure, and we will ask you some questions of how this should look like to you and what the requirements are and the functions are that you would like to see in the future. And then we'll try to see how we can bridge that with RENA. The survey would be online by the end of the year, and we hope for in a good two to 3 weeks. And the deadline for input would be somewhere at the end of January or somewhere in February next year. So you have a good 1 to 2 months to complete the survey. So thank you. So that was the arena.
A lot of stuff there. Very interesting also. One single question?
Maybe about tomorrow, what's the focus tomorrow about the more in-depth discussion in RENA?
Normally I would try to ease you into how we got to this architecture, because right now I just started from the architecture without, well, I try to give you some background, but as you asked, we will go through the architecture, which would show you where some things went wrong, and actually why we came up with this recursive architecture, and why we defined these and these and these functions and not other functions. So that would be the talk for tomorrow.
It's great to have some time there for discussing it, and it's definitely a way of changing the way that we think about the network. I think we will then continue to
Yes.
Anna, representing the MOMAT. And the microphone.
Oh yeah, sorry.
I don't know why everybody laughs when they see this. It's cute.
I like hands.
Is it on?
Yeah.
Okay, so my name is Anna Fagertun, and I'm from DTU, the Department of Photonics Engineering. Don't ask why the Department of Photonics Engineering has a networking group. That's just where we were placed. Me and my colleague Martin and a colleague from this very complicated to pronounce German institute won this open call for creating a multi-domain optical modeling tool. And I will tell you a couple of words about this tool now. I will present you the MOMOT in a nutshell, then I will have exactly one slide for the consortium because we are not that many in it, and then I will very briefly go through the structure of the project, and then the majority of the presentation will be on our vision for this tool and how we plan to address the challenges. So MOMOT, why does it sound like so strange? Basically, we just took the main letters of the open call name, and it just turned out to be a MOMOT. So it's kind of funny, but we liked it, so we took it. We are going to be doing a multi-domain optical modeling tool. And the goal is, as a first, to realize what are the needs within the NRAN community for such a thing. The project is focusing on something called alien wavelengths, and alien wavelengths have been within the GIANT at some level for several years now, but we got the feeling that there is still not a clear understanding of who needs it, why they need it, how they need it, do they need it at all? So we pledged to make a survey and say, okay, let's figure out, is this really needed or isn't this needed at all as a service? And then, of course, we would like to develop a tool that will assist the NRANs into evaluating and assessing the deployability of an alien wavelength in their network. Can they or can they not, and under which conditions, and how they can do that. We have 3 phases in our project. We will start with gathering needs and requirements and design specifications, and that will also be done as the previous project by surveys. We're going to need your input for this. Every NREN, we plan to address as many NRENs as possible. If we can address everybody, that would be great. To figure out, do you need this? Do you see a future for this? What do you think about it? Just really very general understanding about the area wavelengths within the different NRENs and within the different GEAN participants in general. Then based on all this information, we're going to design our tool with its input and output parameters and interfaces and so on. And then of course we're going to implement it, validate it and test it, and hopefully by the end of these 18 months we were going to have something that is usable and valuable for the community as a whole. Yes, we started in the 24th of October, so kind of a month back. So we are still at the beginning of this journey. So, what are area wavelengths? Some of you might not really know what this is, so I decided to give a very general definition here of what is an alien wavelength and how we, within the project, see an alien wavelength. But this is an optical signal from a third-party transponder that is carried within your WDM infrastructure. So if you are not operating your WDM infrastructure, I would understand you saying, okay, this is not for me. But actually, we would like to know that if this is not for you. In general, if you have a WDM domain like a, let's see here. If you have a domain that has been provided by a vendor X, you can plug a transponder from vendor Y. If you, let's say you're running Siena and you're plugging an Alcatel-Lucent transponder into it. This is an alien wavelength. It has its own advantages. It also has its own disadvantages. There is plenty of literature out there that you can see. There are a lot of cases that has been reported, a lot of field trials that have been reported. So it seems to be usable. There seem to be people that are interested in this, specifically for reducing cost and for creating multi-vendor interoperability. And what our tool is planning to do is sitting on top of all this and trying to evaluate, okay, is this alien wavelength, can we put it from here to here, or we cannot put it from here to here. The consortium is kind of small. We are only 2 partners, Dimitri, where we will be the project coordinator and we'll get the requirement specification and of course the design of the modeling tool. We will get some help from our other participant, but this is our main responsibility within the project. As Paul said at the beginning, this is me and my colleague Martin that are responsible for this. Martin is the project coordinator, so but I'm also ready to answer all questions that you have, or ready to take all the comments or all the criticism or everything that you would like to throw at us. I'm very easy on that. I would actually prefer that you come up with some criticism so that we can really create something that is usable for all of you. Our competences are within multi-domain networking and within using modeling tools at the networking layer, physical layer, and so on. So we feel that we are quite fit to solve this task for the GEAN community. And the other partner, it's GWDG. I'm not going to even try to pronounce the real name, but this is a center in Göttingen, in Germany. And from there, we will get the modeling tool implementation. Some very clever guys are sitting there that can do this, and they can do the validation and the verification. And our contact person from there is Siamak. He has a very extensive know-how into and experience into how to design physical layer modeling tools. He has been involved in the FP7 DicoNet project, which has done something within these lines. So we're going to use his expertise in the field, so we can really bring up a good value within this project. The project structure, considering this is only 18 months small project, we have only 4 work packages. We have, of course, general management and dissemination, the requirement specification and the modeling design and implementation, and at the end we have the performance evaluation and validation. I decided to show this organizational structure here simply because I wanted to underline that we decided within this project to have an advisory board, and this advisory board we have called experts from industry, academia and NRENs, also people from outside GEAN that we have included in our advisory board, in order to give us an overview of, okay, is this really relevant, or is this some kind of just a NREN topic, and so on. We of course will be very willing to hear all inputs from anybody that would like to give input to this advisory board. The vision for this tool, I have decided to take some sentences from our proposal. So the vision is that we should develop a tool for the GIAN community, which of course should be a little bit more than whatever is existing out there today, and that can estimate and predict the alien wavelength performance within the network, and also assess the implications of this alien wavelength on existing services, which has been outlined as one of the biggest challenges within this technology. Then the tool should of course rely on as much detailed information as possible about the network, and we know that each network is different. You use different architectures, you use different vendors, you use different operations. That's why the idea is to come up with some kind of a unified description of the input towards this tool in order to be able to have something usable. We cannot fit the tool to every single network out there and every single vendor and every single technology. This of course will be done within the first phase of the project, where we are gathering the requirement specifications and the input from the NRENs. And of course we would like to be vendor independent. It doesn't make sense for us to design a tool that only fits Sienna equipment or Alcatel-Lucent equipment or Adva equipment or whatever you're using in your WDM layer. It is very important for us to underline what we are not going to provide with this tool, because there has been some confusions and people asking us in previous venues, okay, is this really what you're going to do? No. We are not going to provide an interface for actual alien wavelength deployment. This is not going to be a tool where you can go and say, I would like an alien wavelength from A to B going through C and D, click a button and miracle happens. That's not what we are going to do. This is not really within the power of 18 months of 3 people project. Yeah, Henrik, you may be able to do it, but we cannot. Then this is not going to give guaranteed performance metrics. So if we give you a quality of transmission parameter of X, it will be within plus minus around this X. We cannot tell you it is going to be exactly 5. And this is simply because it is a little bit difficult to gather up all the possible setups in all the possible networks into a database. It's difficult to get all the possible equipment, vendor equipment specifics, and so on. So it is unrealistic simply within these 18 months. It is unrealistic. So we have decided to make a tool that is usable for the NRENs and that is realistic, so people don't get disappointed at the end. Of course, all this can be done. It's not that they cannot be done. They just cannot be done within 18 months. So if the MOMOD becomes a success and it becomes usable within the NREN community, the tool will be free for everybody to extend and to build on top of it. It's going to be open source, so it will be possible to develop it further to include those functionalities. So how will it look like? This is a very high-level view, but it describes the flow of operation of this tool. There's going to be a demand structure here that takes some input. Let's say you would like a path from A to B, and we need A and B. I mean, we cannot give you a path from nothing to nothing. We need this as information. Then there's going to be some repository or network topology and physical parameters repository where we're going to extract information from, combine it with this demand, run a quality of transmission estimation and a path computation function, and then come up with a path and a quality of transmission indicator. So this is basically very, very simple way of presenting the tool. So these parameters that constitute the demand structure, they may include, but they're not limited to, of course, the source and the destination. Maybe if you would like to have a disjoint path for survivability purposes, for protection. If you would like to fix the alien wavelength frequency, let's say, okay, I do have this frequency specifically and I cannot deviate from it. Can you accommodate it in your network? Some input power, physical layer parameters, maybe an application code taken from ITU-T specification, the G698.2 is working with alien wavelengths or similar concept, and of course other parameters that can get into the into play. And these input parameters, they should come from you, the users, and we're going to gather them through our surveys through the first phase of the project. Then we have the core module. It will make the important part of the estimation tool. We'll have path computation that is going to compute a path through the network, so we will need the network architecture as such. Then we will have a QoT evaluation, and this block will utilize, now don't hang me for these words here, there. I'm not a physical layer person, so don't ask me anything about this, ask my colleagues, and I'll probably relay the question further on, but we're going to use something that is called a nonlinear Schrödinger equation, which I don't even know how it looks like. But Siamak knows, and he's going to be the one implementing this. We're going to use a lot of analytical models for the evaluation of the different parameters, and we're going to use lookup tables. The plan is, for example, the ITU-T specification here has nice values that they specify for interoperability, or some offline computation tools, or some well-known parameters for the given network, and so on. And all this is going to be implemented in C and an open source version of MATLAB, and it will be available for for everybody that in the NRAN community that would like to use it or extend it, and so on. And we're going to make a web-based interface, a web-based tool. The tool will be web-based, so that you can use it from home, so to say. The idea for having this repository is that we do need a very detailed description of your own network. If you would like us to tell you if an alien wavelength is suitable for your network, we need to know what your network is. And we need to know the topology, the link and node connectivities. We need to know physical parameters, for example, what kind of fiber are you using. We need to know description of the links, dispersion, for example, in them. We need to know existing light paths in the network, or at least neighboring light paths in the network, so we can calculate possible interaction between the alien wavelength and the existing services in the network. And we're going to tell you, okay, this is your path. If you want an alien wavelength through your network, you should pass through these nodes and not through the others. This is going to be the impact of this alien wavelength on your existing services, and this is going to be the performance of your alien, or plus minus performance of your alien wavelength. Maybe we can give a k-shortest path, or a 1+1 protection path, or something similar if it is needed. And all in all, the idea is to provide an overall network performance evaluation for this for the alien wavelength. So we have less than 18 months for this challenging task, and the tool, again, I would like to emphasize, is going to provide an indication and not guarantees for the performance. Alien wavelength deployment is historically a custom engineering task. Those of you that have been involved in trials and deployments, they know that it is very much custom engineering within the network. And we need a lot of input from you, of course. The tool is for the NRANs and for the GEAN community in general, so we need to know what you need in order to fit our tool design to it. Even if your organization is not running the WDM infrastructure, even if you're not running wavelength services within your organization, we would like to hear from you and would like you to fill in our questionnaires and say, okay, there's going to be a first question, do you use alien wavelengths? You can just say no, and that will be fine, because we have pledged to gather up a very comprehensive overview of the needs within the community for this technology, and it would be very nice if we can get everybody to answer. We will try to make this survey as short as possible. As far as I know, it's about 10 questions right now, so it's not going to take much of your time. So please fill in the questionnaire when you receive it. Thank you.
Question or two, Rainer?
Yeah, only an additional remark that this last statement by Anna is very important, that today or tomorrow we should make a definite choice how to address the entrance for this question. We have had a discussion with Dante about it. Should we use the APM list or should we use just a neutral NRN list, or maybe we can discuss today and tonight with people around here from NRNs what is the best way to do this, because you really like to have some valuable feedback.
Yeah.
During the General Symposium in October in Vienna, we have already exercised this 4 or 5 NRNs in a let's say one-to-one relation.
Yeah.
But from this mini project, we really would like to address more NRNs. So give feedback on that, yeah, and tell us, or tell Anna, what's the best way to do this.
Yeah.
Do you have the list of parameters which do you need?
No, and we are going to ask you when you say, yes, I'm interested in alien wavelengths, 3 weeks later you're going to get another survey, and then we're going to ask you, okay, tell us what you're interested in exactly, how your network operates, what parameters are you interested in. And then we're going to make a common list and say, okay, the tool will meet these X parameters because they are most relevant for everybody.
You are going to make the tools.
Yeah.
In this tool, you may actually you need some parameters which you know maybe already. But your tool depends on some inputs and you have some outputs.
Yeah. I think this with the input is a very, very interesting question as well, because I mean, as I said here, the demand structure may look like this. For example, the alien wavelength frequency might be an input parameter, but it actually may be an output parameter. If you tell me I would like an alien wavelength for point A to B, then the tool will tell you then it needs to be on this wavelength. I cannot accommodate anything else. And then the frequency will be an output. It's not going to be an input.
For instance, you need to know the type of modulation.
Yes. All these from the node and link types we need described somehow. And this is of course part of the work we're going to do. How to describe a node and how to describe a link, so that the tool can use this information for quality of transmission estimations. Okay, there was a question there.
Regarding the definition of alien wavelengths, how do you see this as service, and who would make use of this? Speaking from my own experience, I was discussing at a certain moment in the context of FIRE with people of CTDC that have an optical transmit. In the UK at the time, the people at Essex, they have also an optical transmit. We are also building one. So there I see some use for alien wavelengths, that you have a transparent connection.
Yeah.
But what do you get then as service, as end user? Is it really transparent then that you have only 1 R regenerations, so just amplification, or?
Yeah, the idea of the alien wavelength is that you do not go to the digital layer. It is.
As a service, you get then a certain frequency band.
Yeah.
A power level that
Yeah.
you may not exceed. And
Yeah.
that's it then.
Yeah, that is what would be as a service. So you can have a cross-domain. That's why it's within the multi-domain topic. You can have a cross-domain transparent service.
Applications then interconnecting optical transmitters?
Yeah, I can actually refer you to a survey, or it's not a survey, it's like a white paper that we have made here a couple of months ago that is on photonic services, part of which is an alien wavelength as a service, and I can refer you to this. It's a 15-page document that describes future applications and possible applications for such services. Okay.
Then we have, I think we have to stop questions now. We have one single presentation from the meal project before we should have lunch.
Before our meal.
And I've said, since I'm presenting it, that he's the one to decide when we're all going to have lunch.
Okay, so let's talk about meal. Some of it over there, some of it over there. Okay, so I will be doing this presentation on behalf of Frans Panken and Marco Leri from Sutnik and Janet, respectively. So this is the project that has not landed within
The mic.
Oh, okay. The mic.
Or there.
Well, okay. This is about the project that has not landed within our GRA, but because it had the eduroam keyword in the title, it landed within GRA 3, and the project coordinator is Stefan Winter. So, but generally it was discussed in the kickoff meeting, and as an interesting development of the network technology for the aggregation of mobile network. So, but it spun off into the open call. So, first objective is to provide the framework for using the eduroam over the third party over the 3G and 4G mobile networks, which is not that simple because eduroam does not also imply the network service, but it also implies the authentication federation and certain privacy rules over the authentication data, which may not necessarily hold for the 3G, 4G networks. Although there are some research networks that have implemented their separate authentication over 3G network, for example, implemented the APN-based like authentication, but it's not necessarily compliant with the current eduroam policy. The goal of the project is to demonstrate the interoperation between the United Kingdom and the Netherlands, so that the users from UK may come to Netherlands, to Amsterdam or to Utrecht, use their credentials, use their eduroam credentials to authenticate onto the mobile network and receive this data transfer service with the different charges, basically, to be able to use the data roaming, really. Because now it's a bit pricey. So, but also not also to reduce the costs, but also to use their home credentials to log on to the network and have the service. And also the international mobile network code and so on. So the best part of it will be really the proof of concept if the eduroam policies can be extended towards the mobile networks, and to demonstrate the multi-domain case. So there are two technical approaches. One technical approach is the APN based, so that the network, the research network, established their own APN within the 4G network, not the 3G network, and authenticate and ask their users to use that particular APN and authenticate there. And the second approach is to use the mobile virtual network operator for the research network to become a mobile virtual network operator and use their own LTE backend to handle all the users, both eduroam authenticated and not. It's based on once you have your own virtual LTE backend, you authenticate not only users, but you have your own devices. You sell the sell or give away the SIM cards, so you have you have more ways to authenticate users as well. So the thing is that users have to basically, this is an illustration of what I was talking about. Users have to authenticate with a local APN, which then gets authorization from the home institution of the user, and that's the other way around. So that this can work, this is to prove the concept that it can work internationally. So that in the end, it's rather not actually so that in the end we can end up in the infrastructure where there be common parts of the infrastructure, so to speak, in the whole Europe or maybe worldwide, where you can use APN name eduroam, and you can log or mobile roam or something, and you can log on to this this APN with your home institution credentials. So that well, first of all, the obvious question: do you still need to pass the data to the home institution? This is obvious that we need to find the project has to define the guidelines how not to do that, or maybe some cases where it is necessary. And billing alternatives, and also the roaming agreements, or what is the legal framework between the operators to establish this. Yeah, and how should we change the eduroam policies, or is there a need to establish some other roaming service like mobile roam or mobile eduroam, or to make some extension of the eduroam policies? Okay, and what could be the strategy for the whole giant area? Also, the virtual network operator issue will be evaluated, whatever it has advantages or disadvantages. How should we go on with that? I've been talking about that already. So that's basically it for the project. I'm not very much involved in that. So if you have I would I will try to answer the questions to my best ability, and if I'm not be able to answer it, I will forward these questions to Franz and Mark. Any? No? Then it's, I suppose it's the meal, the real meal. Okay.
Yes, that is true, and thanks for all the presentations during this morning session. We are going to have lunch, it's sandwiches, and after the lunch